In today's film, we're going to talk about the relationship between mass and wavelength. As mentioned in previous films, mass is directly related to wavelength. And the way this is calculated is quite simply by using density, which converts to pressure inside of the vacuum chamber of the pyramid. Pressure is the last stop, so to speak. But essentially, in order to obtain this value, it's the fusion between wavelength and mass, which will clearly be described in the slides to come. So, moving straight to the slides, we have here Planck Mass. This is the true equation for the mass of this universe, the true mass and the one mass that exists as the baseline unit of this universe, which is quite simply square root h times c over g. And that's it. And what's so interesting about this calculation in the way it's used is that it never changes. This calculation is never scaled, or it is in respect, but this value itself is fixed. When scaling the pyramid wavelength, you adjust the physical length, or the Planck length, to suit the wavelength inside of the pyramid. And this is possible only because the corresponding values, like Planck mass, don't change, thus giving it always a reference point to the beginning. So this weight that is generated from the Planck mass being 5.4556 E minus 8 kilograms. So it's actually a conceivable weight, arguably the weight of the universe, as bizarre as that may sound. This weight is in fact one of the most important forces used in the pyramids, the first being length, the second being mass. So this equation, as seen on the screen, never changes, and this weight calculated by this equation does not change when used in the pyramids. Moving to the next slide, this is more like a flow chart to understand how we arrive at pressure from length and mass. So this is how the pyramid converts density to wavelength. So the density inside the pyramid is directly related to its wavelength. This is one way of understanding how. So essentially, when you set a wavelength inside the pyramid and you marry it with its corresponding density, it understands that the two are the same when they are tuned together. So looking at this chart, we start from the left. It says pyramid wavelength, which represents length. So say if we start with a length or a pyramid wavelength, it could be any length in this example, that must be converted to volume. So moving across, that pyramid wavelength simply becomes cubed in order to derive a volume. Then moving across again, quite simply, and it is this simple, all you do is add the Planck mass to this volume. And that is how you derive density. So a density is instantly calculated by adding the mass, the Planck mass unit, which never changes, as shown in the previous slide, to the volume of a cube, which each edge represents the wavelength of the pyramid. So it is the wavelength of the pyramid cubed with the Planck mass inserted within it to derive a specific density. There is one more step required in the calculations because pressure must be derived from density, because pressure is how you physically measure the gas inside of the pyramids. So therefore, by adding a few more inputs, One being the gas constant, in other words, the nature of the gas that you are assigning the pressure to, and temperature is another variable in this equation. So quite simply, by adding together the density, the temperature, and the gas constant, you finally arrive at the answer of pressure. And pressure is where it's at. That is essentially how it is measured on the vacuum gauge. The pyramid is completely evacuated of the atmosphere. It is backfilled with an inert gas, representing the gas constant, or R specific. And then, quite simply, by tuning the pressure, that is how you match the wavelength. By using this system, which you see on the screen, which will be explained in other ways in the coming slides. So you are converting length and mass to pressure. Moving to the next slide. Here we have the equation example. Mass divided by length cubed equals density. And the dot in the middle of the cube represents the Planck mass always. And the length, the side of the cube, as per the previous slides, is the wavelength that's going to be used inside of the machine. In this case, the calculation represents 13.1469 millimeters, which equals a density of 0.024012 kilograms per meter cubed. And I'll explain how this is calculated. But quite simply, for that wavelength, that is the actual corresponding density. Moving to the next slide, that length is in fact 1 Planck length times 2 to the power of 108. So that is your wavelength example. And again, the total amount of gas particles in the cube always equal the Planck mass. So regardless of the equation, the weight of the gas within the frame of the cube will always equal that weight, the Planck mass. And this slide will express that in a visual form of motion, whereas you can see the cube expanding, slowly expanding, and as the frame of the cube expands, so does the wavelength inside of the machine. The wavelength expands, but the mass is fixed. So what's happening here? The density decreases as the wavelength increases, but the mass always stays the same, and it is the Planck mass. So again, as the wavelength increases inside of the pyramid, the density must decrease because the mass is always the same. And this is how you scale the universe. This is the most magical aspect of it. It is the fusion of all things. Length, correspondence to the Planck units, the baseline of this dimension. And because gas can be scaled, quite simply by adjusting the amount of evacuation, this is possible. What's more marvelous is that it is within range of scalability. And here we have some examples, which were references in the previous videos. One being the Planck length, 1.142857, being the systems of 7, 1 divided by 7, and 1.3333, the equilateral system, 1 divided by 3. Refer to the previous videos to understand how these ratios are derived. But this is a visual example of the cube, which represents length and density. And so again, slight variance in length will adjust the density. The density will become lower because the mass is always the same. So the total amount of gas particles in the cube always equal the Planck mass. The length changes, the mass is fixed. And here's another way to actually understand how it stacks. So both of these examples are within the same volume as expressed. And what's happening here is that as per the octave, the law of octave, there is also law of octave with density and stacking density. So say if we have one wavelength to the left, which is 26.2938 millimeters, and we move to the right, and instead of having a wavelength of 26.29 millimeters, we've chosen to have a wavelength of 13.1469 millimeters, which is half of 26.2938 millimeters. And so as a result of this, the density is 1 octave greater. Now with octave, it is doubled or halved, but with density, it is to the power of 8. Because 8 of these cubes, if they are half the wavelength, fit within the same volume 8 times. And this is a rough attempt at showing this in 3D, which is a little bit hard to see, but what it's supposed to represent is that there is 8 times the amount of density within the same cube. And the wavelength, being half, automatically assigns this because there is 7 leftover spaces to fill the same volume. So this is stacking density. So as a simple visual tool, the density of the wavelength to the left is 8 times that to the wavelength of the right. The wavelength to the left is 26 millimeters, and the wavelength to the right is half of that, being 13 millimeters. So that is how it can be seen stacked as per the octave, but in this case with volume, because we are dealing with density. This slide represents exactly the same thing, but it is represented as a dot, representing the Planck mass, which in the previous slide was representing gas particles. But it is actually the same system, but visualized in slightly a cleaner way. And now what we have is the actual equation and the outcome for a specific wavelength. The equations will be run through using the computer and how I actually calculate them, but essentially this is solved for 1 Planck length times 2 to the power of 108 equals 13.1469 millimeters. So for a 13.1469 millimeter wavelength, using argon, which has an R specific or a gas constant of 208.13 joules to kilograms Kelvin. At a temperature of 20 degrees Celsius equals a pressure of 10,988 microns of mercury, or approximately 98.5% vacuum relative to atmospheric pressure. And so using this method, that wavelength equals that pressure using argon at 20 degrees Celsius. And that is the outcome. And so what's also very interesting is that the wavelength range that is needed to be used inside of the machines is in fact very easy to achieve. It is in between atmospheric pressure and the vacuum of space, and is very easy to achieve using conventional vacuum pumps. And here's a chart for curiosity. This is actually some rough calculations that I did to show some elements and materials and their corresponding wavelength. So gases can be scaled inside of a vacuum chamber to match a wavelength, but materials that are fixed, such as the densities of water and solids, they have a fixed wavelength which cannot be adjusted because the density for these materials is also fixed. So this is a chart for visual curiosity for people to understand what wavelengths correspond to what materials found in nature. So looking at the example we used before, the Planck length times 2 to the power of 108 has a density of 0.024012 kilograms per cubic meter. And that is the corresponding wavelength, 13.1469, so the same. But moving to things found in nature, or materials and substances found in nature. For example, air at Mount Everest has a density of 0.426 kilograms per cubic meter, which means that at Mount Everest it has a corresponding wavelength of 5.04 millimeters, scaled up from the Planck length. Air at sea level, which is denser because it is closer to Earth, has a density of 1.225 kilograms per cubic meter. Because it is denser, the wavelength is shorter. So at the surface of our Earth, we have a wavelength of approximately 3.54 millimeters recognized by the Planck units. Water, which is how the kilogram is scaled, so it's exactly 1,000 kilograms per cubic meter, which, because it is much denser than air, the wavelength shortens all the way to 0.38 millimeters. Then quartz, with a wavelength of 0.28 millimeters, and then copper, denser yet again, a wavelength of 0.18 millimeters. And so as a visual tool, as density decreases, wavelength increases in length, and as density increases, wavelength decreases in length. And here is a slide just to show how this visually looks. Density is greater at the surface of the Earth, and as you approach the vacuum of space, higher and higher in altitude, the density decreases. And I've chosen this slide because it has the particles so that you can visually represent this and understand that the sparsity of the particles also represent greater length in wavelength. This is a vacuum gauge to show that this needle will move close to the end, or 98.5% of what was shown in the previous example, which is actually a very easy vacuum to achieve. It is only in the high vacuum range, past 100 microns, that it begins to be hard to achieve vacuums at that range, which is above 99.99% vacuum. And lastly, just to show the pyramid chamber and the fact that this is a vacuum chamber means that it is a separate and artificially created atmosphere which allows for the gas to be scaled inside. And this is why the pyramids are always housed inside a vacuum chamber. And now you understand the vacuum chamber's function and why it is crucial as a requirement to build successfully working pyramids. So basically what I've set up here are a whole series of calculations that I use for calculating these values. And the reason I use calculators is to prevent error. I prefer to use calculation. I prefer to use calculators to do the calculations because I do a lot of calculations and I find that you come across less errors by simply double checking your calculations using calculators. It's especially handy if you're calculating all day long, which sometimes I can be doing this. So this is a cube calculator. So we start off with translating length, or the wavelength that we desire, to volume. And you can do this very simply on a calculator, but nonetheless I will use this calculator just to show you the actual outcomes more than how to do the equations. The equations are self-explanatory because they are documented out, but there are 1,000 ways to do them. For simplicity's sake, we'll be using calculators to do these. So this is the Planck length times 2 to the power of 108, which gives you a value of 13.1469 millimeters. So that is one of the lengths of the edge of the cube, representing the wavelength, which calculates to a volume of 2,272 cubic millimeters. That is the value. So that is the value you need to move on to the next part of the equation in the way I'm calculating it. So, using this calculator, which is a density calculator, starting with the Planck Mass, the true value for the Planck Mass, which is 5.4556 to the power of 8, negative E minus 8, kilograms. So this is your Planck Mass, which never changes. Never ever does it change. It is locked and fixed forever for all calculations in regards to this. So taken from before, the volume, 2,272 cubic millimeters from the previous calculation we did to convert that length to volume, which gives you a density of 0.0240 kilograms per cubic meter. And that is your density. So we have solved density for length, quite simply. So for the Planck length times 2 to the power of 108, this is your density, which was depicted in the slides previous. Moving on to my favorite, here we are. Before we move on to the next calculator, I'm just showing you here the chart for the R specific of argon in joules, kilogram, Kelvin, which is the way it is measured. This is the R specific, which is 208.13, which we'll need to punch into the next calculator. Now this is the final calculation, which this is an ideal gas law equations calculator. The equation that we'll be using in this calculator is here. This calculator quite simply does all of this for us, which at the very end of all this, what we need for all of these inputs is pressure. We're trying to solve for pressure, because pressure is how you physically adjust or measure the vacuum inside of the vacuum chamber. So you need pressure because that is where it is. That is what the gauge will tell you, and that is why we need to punch all of these inputs in to solve for pressure. So from the previous calculator, we have punched in the top here density, which we derived from the other inputs. So this is our density. So we need that as the first input. So for that wavelength, the Planck length times 2 to the power of 108 equals this density. Then we have to punch in the gas that we're using. So we're using argon, which has an R specific of 208.13 in joules, kilogram, Kelvin. And finally, for these calculations to work, we must also punch in temperature because that is a variable. In this case, we're just using an example of 20 degrees. Planck temperature can be calculated, but it is not required for these calculations. So we're using 20 degrees Celsius here. So this is in Celsius too, by the way. And so therefore, if we hit calculate, which I believe it already is, or has been done, we move down to the measurements which I use, which is millimeters of mercury. That is the measurement I prefer to use because that is the gauges I use this, and I'm familiar with it too. So millimeters of mercury. And so for all of what we just calculated, we get a final pressure measurement of 10.988 millimeters of mercury. Now, the digital gauge that I use, and most gauges that I use, are actually measured in microns of mercury, not millimeters of mercury. So we quite simply put some extra zeros under the end of that and get 10,988 microns of mercury. So, quite simply, as mentioned before, the Planck length times 2 to the power of 108 using argon at 20 degrees Celsius gives you this pressure, 10,988 microns of mercury. And that is quite simply how these equations derive pressure. And pressure is what you need to know to scale the machines. Pressure at a specific temperature. And this is how I calculate it. There are many ways to do it, but this is the way that I have been doing it for years. And this is the way I prefer to do it because I am very familiar with it. And mistakes are prevented in the process. I also created a very strange and crude calculator based on the way my mind works. I decided to create a calculator in AutoCAD using specific curvatures of lines. And in this calculator, the different lines represent the different gases, the different inert gases that the pyramid uses, or that can be used in the pyramids. Mostly focusing on argon though. This calculator quite simply converts length to pressure. And the way it does that is through the specific curvature of these lines, which represent the R specific of each inert gas. So this is an approximate calculation because I could only get these lines so accurately, but quite simply, this is wavelength, starting from this bracket here, moving upward, and quite simply when you have found your desired wavelength, for example, here, 15.75 millimeters, you quite simply mark that, measure it, which in this case it already has been, and you measure perpendicular to that. And where it stops, so if we zoom in, we get 6.52 millimeters, which with an extra 3 zeros on the end of that, or moved 3 decimal places, I should say, gives you 6,510 microns approximately. And so for interest's sake, I just made this so I could quickly calculate ranges of different gases, or these 4 different gases. And I think, no, helium's not in here, but it was in another one. This gives me a quick reference to convert length to pressure without having to go through those other calculations, but for more accurate calculations, they'll be done correctly using the calculators. Well, after all that, I hope you enjoyed the video. I think it's an exciting subject, and when I discovered these things, I was very excited myself. I'm yet to put them to practice, but again, I need a group of people to help me do this, for it is dangerous to build these machines alone for the first time, especially if they work.